All right, ladies and gentlemen, welcome back to one of our last videos we're going to be doing this year. This is our talk of a difficult concept in physics called mechanical energy. Now, mechanical energy seems really simple when you first hear about it, but then when you start to look at the types of problems that we ask about it, it becomes more and more and more confusing. All right, so mechanical energy, in terms of what it is quite simple. Mechanical energy is the total amount of potential and kinetic energy that an object has. So we've done both types of energies this week, and when we add them both together, that's mechanical energy. It's super simple. When you look at the formula for it, mechanical energy, EM, is equal to our potential energy plus our kinetic energy. What makes mechanical energy super confusing and kind of annoying to deal with is a very important law in physics called the law of conservation of energy. Now, the law of conservation of energy is similar to the law of conservation of matter that we saw back in chemistry, right? Basically, what it says is the amount of energy an object has can never be created or destroyed. It can only be transferred or transformed. In other words, whatever energy something starts with, it can't get more or less. We can't just create energy from nothing, and we can't remove energy that exists. It can be transferred to something else, and it can be turned into a different type of energy, but it has to go somewhere. That energy doesn't just disappear. So the only way that something can lose energy is to do work to something, to give energy to something else. You can't just eliminate energy that you have. In other words, and this is what's going to be really important for us, however much energy something starts with, that's how much it should end with, unless it did work to something. But we're not going to worry about that in Science 10. All right. So however much energy something begins with, however much mechanical energy something has, should always stay the same. It doesn't matter what's happening to that object. As long as it's not doing any work to anything, it should keep the same amount of energy the entire time. However, the type of energy it has, whether it's potential energy or kinetic energy or a combination of both, should stay the same. Now, the energy can transform from potential into kinetic, and it can turn from kinetic into potential, but the total amount of energy that something has needs to stay the same. All right, and that's going to be really important for us. It's going to create a lot of confusing situations that we'll go through together, but overall, that's the law of conservation of energy. So our formula for mechanical energy, as I said earlier, is simple. It's our potential energy plus our kinetic energy, or another way of writing that is mechanical energy is equal to our mass times gravity times height plus our mass times velocity squared divided by 2. Basically, it's our potential energy formula plus our kinetic energy formula. And on the first surface attempts at that, that's very simple. And we'll look at some simple scenarios with that, but we'll see how that gets confusing in a second. All right, so in case you wonder where mechanical energy fits in and why it matters, let's think about something that you guys should be relatively familiar with, which is a bird flying across the ocean. All right, so imagine that this beautiful green circle here, this is my bird, all right? And it's going to fly this way, okay? And so because it's flying that way, it's got a velocity, right? It's moving. That means it has kinetic energy. So our kinetic energy here is going to be equal to the mass of the bird times how fast it's flying divided by 2. All right? So this bird, because it's moving, has kinetic energy. It's got some sort of velocity, and therefore, because it's moving, it has a kinetic energy. But it also has potential energy, and we know that because the bird is above the ocean. Okay? So however high the bird is, it also has potential energy because its potential energy is equal to the mass of the bird times gravity times height. So the bird has two types of energy. It has potential energy because it is currently floating above the ocean. It's got height, which gives it energy, and it's moving, which gives it energy. So it has potential and kinetic energy, and so the mechanical energy, the total amount of energy that the bird has, is going to equal how high it is off the ground in terms of its kinetic energy or potential energy plus how fast it's moving in terms of its kinetic energy. So the mechanical energy is a combination of how high the object is and how much it weighs, and how fast it's moving, and also how much it weighs. And so these two things are going to factor into one another in simple ways, but also very odd ways. Okay, so everything I've talked about so far is actually relatively simple. We get the idea: if something's moving, it has kinetic energy. If something is up high, it has potential energy. The total amount of energy it has, the mechanical energy, is those two things added together. There's nothing difficult about what I just explained. The trick comes in when I bring in that law of conservation of energy. All right, remember, however much energy something starts with is equal to how much energy something ends with. All right, and so what gets confusing is the idea that the total amount of energy that something has should not change unless it's doing work. And we're not going to worry about cases where it's doing work, so let's not even worry about that at all. So imagine the following scenario. Imagine that this little green circle, instead of being a bird this time, is now a rock, right? And I'm standing on the top of this cliff up here, and I'm going to hold this rock in my hand, and I'm going to get ready to drop it into the water down here, okay? Now, when I first have this object in my hand, right now, it only has potential energy, right? Because at this moment, right before I drop it, it only has height. It's not moving. I'm holding on to it. It's standing still. So it has no kinetic energy whatsoever. So the total amount of energy it has is just the potential energy that it's getting from the mass of the rock times gravity times height. It has no kinetic energy, okay? It only has potential, which means that the total amount of mechanical energy it has is just potential energy. It has no kinetic energy, so the only energy it has is just the fact that it's standing off the ground, all right? Now, hopefully that makes sense to you. It's not moving, so it can't have kinetic energy. Mechanical is potential plus kinetic, and if it has no kinetic, then its mechanical has to be the same as the potential energy. Imagine I take that rock and I drop it. It starts falling and falling and falling and falling, and eventually, falling and falling and falling and falling, and eventually it's halfway down, okay? What I hope you guys understand is as something falls, its height turns into velocity. Or a better way of phrasing it is that its potential energy it had from being up high turns into kinetic energy because as it falls, its height turns into speed. It speeds up the more and more and more that it drops, and its height, because it's going down, means it's losing potential energy. So anytime something falls, its potential energy gets converted into kinetic energy. So imagine that this rock is halfway down. Now at this point, it's got, of all the energy it has, 50% of it, if it's exactly halfway down, is potential energy. Okay, so 50% of its energy that it started with is now just in the height that it has. And the other 50% is kinetic energy. Okay, because its height that we started with has turned into speed. So its potential energy has turned into kinetic energy, which means that these two things added together are still equal to the total amount of mechanical energy, which is still equal to 100% of all the energy it has. So as this object drops, potential energy turns into kinetic energy, and a better way of thinking that is its height turns into speed. It gets faster and faster the more it drops. Okay? If I continue this rock along its pattern right at the split second before it hits the water, when it has zero height, what that means is that at this moment, its potential energy is zero. Okay, because it has no height, and because potential energy is mass times gravity times height, if I have a height of zero, that means I have a potential energy of zero. All the energy that this rock has in the very split second before it hits the ground is 100% of all the energy. In fact, all of its height has turned into speed right before it hits the ground. And again, that total energy is equal to my mechanical energy. And if I follow the law of conservation of energy, what that means is the total amount of energy I start with has to equal the total amount of energy that I end with. And because what I started with at the top here was all potential energy, and the energy I ended up with at the bottom here was all kinetic energy, what that means is however much potential energy I had at the top of the cliff has to equal all of the kinetic energy that I have at the bottom. In other words, what's happened is all of the height this rock had has now turned into speed. It has no more potential energy. It all got converted to kinetic energy. But however much kinetic energy I had at the bottom has to equal the potential energy at the top. In other words, EP at the top has to equal EK at the bottom. And this is because of the law of conservation of energy. The idea that the amount of mechanical energy something has cannot change, but what type of energy it has can change. Okay? So we're going to go through a few example problems here. The first one we're going to do is very simple, and we're going to do two more that are a little bit more complicated, bringing this idea into it. All right, so let's look at our first problem with mechanical energy. And with any mechanical energy question, you're going to notice a few things that stand out right just from reading it. So let's go through them. You have a 0.300 kilogram baseball that is thrown in a straight line through the air at a height of 2.5 meters at a speed of 20 meters per second. What's the total mechanical energy? All right, as soon as you see the word mechanical energy show up, you know that you're going to have to deal with both potential and kinetic energy, and basically just figure them both out and add them together. The other way that you can tell that you're going to have to use both the kinetic and potential energy formulas is the fact that it gives you a mass. Okay, that's common in both formulas. You're given a height, that's in the potential energy formula, and you're given a speed, that's in the kinetic energy formula. The only thing we're missing here to solve potential and kinetic energy is the fact that we need gravity, but we know that gravity is always 9.81 meters per second squared. So every mechanical energy question has a minimum of 2 steps to it. We need to find the amount of potential energy this thing has, then the amount of kinetic energy it has, and then just add them together. It couldn't be easier than that. Okay, so let's go through this together. We know our mass is 0.300 kilograms. It's going to be important for both formulas. We know that our height is 2.50 meters. That's good for us to know for potential energy. And we know that our speed is 20 meters per second. And that's good for kinetic energy. Now, it doesn't say in the problem, but it's not always bad to write down like, hey, I'm given mass and height. I also know that gravity is 9.81 meters per second squared. And notice that we're not using negative. We've talked about that a bunch over the last 2 weeks. Energy can never be negative, so we're not going to use a negative there. And it's asking us for the total mechanical energy. All right? So we're going to break this down into 2 steps. Step 1, which I'll do in yellow, we're going to find the potential energy, because I find it easier, so I like to do it first. So potential energy is equal to mass times gravity times height. So we're just going to plug our numbers into that. So we're going to go 0.300 kilograms times 9.81 meters per second squared times our height, and I think I need to zoom out because I can never write small enough for these formulas, times our height of 2.50 meters. Okay. Now, when I plug all that into the calculator, I get a potential energy of 7.3575 joules. Now, I'm not going to round that right yet. I'm going to wait until I've added the potential and kinetic energy together because I want to make sure that I'm not rounding until the very end. So I want to keep that number in my calculator. In the meantime, let's figure out kinetic energy. So kinetic energy is equal to mass, there we go, times velocity squared divided by 2. Plug my numbers in again. So I'm going to go 0.300 kilograms times my velocity of 20.0 meters per second squared divided by 2. Okay, sorry about that second underline there. And when I do that, I get a total kinetic energy of, sorry, I'm just looking at my notes here. There we go. I'm looking in the right spot now, of 60 joules. All right. So now, to figure out the total mechanical energy I have, remember that mechanical energy is my potential plus kinetic. So I'm going to go 7.3575 joules plus 60 joules. Okay. And when I do that and I add those two together, what I get is 67.3575 joules. I have to round that to be the right number of significant digits. So if I go back to my original numbers, and whenever you have a multi-step problem, just go back to your original numbers. When I go back to original numbers, both of these had 3 digits in them. So I'm going to round my answer to be 67.4 joules. Okay. Now, I'm doing this as I look at my answer key, and I realized I used the wrong number of significant digits in my answer key, and that's okay. Just remember to be careful of that in the future. Whenever you have a 2-step problem like this with multiplication and addition, just go back to the original and use the multiplication rules. So this should be the correct final answer here with the correct number of significant digits. All right, so that last problem wasn't too bad, but this next type of question, which is question number 2 on page 13 of your booklet, is a little bit trickier because it's going to involve that thing I talked about before with the law of conservation of energy. All right. So in this case, we have a rock that is 1.50 kilograms. Okay. The rock doesn't change weight between the top and the bottom, so that's great. It's at the top of the cliff, which is 30 meters above the lake. And what it wants to know is what is the speed of the rock just before it hits the surface of the lake. All right. So this is the type of problem that gives students headaches. And the reason is a lot of times students don't know exactly what to do to solve this question. The reason you don't know what to do, or you might, but the reason students don't know what to do is because it gives us mass, great, and height, great, and we always know gravity, great. We could find potential energy of this rock, perfect, but it's not asking for potential energy, it's asking for speed, okay? Now, speed comes from the kinetic energy, so what you need to realize is that at the very beginning of this rock's trip, from the very top of the cliff as it down to the very bottom when it hits the surface of the lake, is that it's the amount of energy, or not the amount of energy it has is changing, but the amount of potential and kinetic energy it has is shifting, okay? So whatever mechanical energy it has at the top has to equal the mechanical energy at the bottom. So in other words, this rock will not gain or lose energy as it falls, okay? But at the very beginning, before I drop it, it only has potential energy, and at the very bottom, as it hits the lake, it only has kinetic energy. And that kinetic energy at the bottom has to equal the potential energy at the top, okay? Because the total amount of mechanical energy that this object has cannot change. And at the beginning, if it only has potential energy, then its mechanical energy is all potential. At the bottom, if it only has kinetic energy, then the mechanical energy it has is all kinetic. So all that potential energy turns into kinetic energy. So the way to solve this question, and you'll see this a lot, is to find how much kinetic or potential energy it has here, because that will equal the amount of kinetic energy it has here. And if I know how much energy it has at the bottom, I can use that plus its mass to find speed. All right, so it's going to be another kind of 2/2.5 step question. All right, our first step in a question like this is always to find how much energy it has at the beginning, how much energy it has with what we know. All right, so what we want to find is how much potential energy, oops, didn't mean to move everything, how much potential energy it has. Okay, so we want to find its potential energy, which is mass times gravity times height. We know that this thing's mass is 1.50 kilograms. We know gravity is always 9.81 meters per second squared. And we know that its height is 30 meters. All we're going to do is plug those into our gravity formula. So I'm going to go 1.50 kilograms times 9.81 meters per second squared. There we go, that took a while. Times 30, I need a little more room. Times 30 meters. Perfect. And when I multiply those three things together, what I get as an answer is that I have this rock starts with a potential energy of 441.45 joules. Notice I'm not rounding that. That's how much it started with. Okay. Step 2 of this question is realizing that however much potential energy it has at the top has to equal the amount of kinetic energy it has at the bottom. Okay, which means that if this thing started with 441.45 joules, before it hits the lake, it has 441.45 joules, but now it's kinetic energy. And then from there, when we want to find speed, we want to use our v equals the square root of 2ek divided by m. Now we know that our kinetic energy is 441.45 joules, and we know that our mass is 1.50 kilograms, so we have everything we need to solve this question. All right, so our last step is to plug our numbers in. So it's going to be equal to the square root of 2 times 441.45 joules divided by 1.50 kilograms. And when I multiply that out and then divide and then take the square root, what I get as a final answer is 24.3 meters per second. Okay, so you see how I kind of used 3 steps to solve that problem. Step 1, find out how much energy it started with. That's what I did in yellow, all right, because it started with entirely potential energy. Step 2, realizing that the amount of potential energy it starts with has to equal the amount of kinetic energy it ends with. And step 3, then using that number in my kinetic energy formula to find speed. Okay, let's get to one last example today, and this kind of brings both types of questions we just did together, all right? So in this case, we have a 55 kilogram high jump athlete, and he leaps into the air with an attempt to clear the bar. At the top of the leap, the athlete has a total mechanical energy of 3,000 joules and is moving at a speed of 8.33 meters per second. He wants to know how high he was. That sounds funny. He wants to know how high his jump was at that time, at that exact moment when his speed is 8.33 meters per second, okay? So this is no longer a case where all of the potential energy is converted into kinetic, and this is not a case of all the kinetic energy is being converted into potential energy. This is a case of this thing having some speed at this moment and also some height at this moment, okay? And so what we're going to need to do here is figure out, based on everything we're given, the potential energy or the kinetic energy it has. From there, we should be able to figure out how much potential energy it has. And from there, we should be able to figure out the height. So this one's going to take a few more steps. All right, so we're going to go through them one by one. So the first thing we want to do here is figure out the amount of kinetic energy this thing has. And the reason we want to start there is we know the total amount. So if we can figure out the amount of kinetic it has, we can go to the total minus the kinetic to find the potential. And once we have the potential, we can find height. All right, so let's find the kinetic energy to start with. We know that our mass is 55.0 kilograms. We know that our speed is 8.33 meters per second. We're trying to find our kinetic energy for step 1, okay? So what we're going to do is use our traditional kinetic energy formula. So kinetic energy is mass times velocity squared divided by 2. And when I plug my numbers in, I'm going to go 55 kilograms times, I need more space. Why can't I write at the correct size, guys? It drives me crazy. 55 kilograms times 8.33 meters per second. And I'm going to square that, and I divide that by 2. And when I do that, I realize that this object, or this person, had a kinetic energy of 1,908.2 joules. If you guys look at my answer key, you see I had double this number written originally because I forgot to divide by 2. It's a very common mistake. And I caught it because I realized that mechanical is always kinetic plus potential, and I had a higher kinetic energy than mechanical energy. So I caught that based on the numbers I was given in the question. All right, I made that mistake, not on purpose, but it's a nice teaching moment, and it's a nice way to see that. I know this will shock you, but I also make mistakes too. All right, so now we know our kinetic energy. We know that potential energy, besides the mass times gravity times height formula, potential energy is also equal to our mechanical energy minus our kinetic energy, right? Because remember that our formula for mechanical is kinetic plus potential, so it follows suit that potential is mechanic minus kinetic, right? We know our mechanical energy is 3,000 joules. Now I'm writing it this way just to save on space, okay? So all I'm going to do in my formula is go 3.00 times 10 to the 3 joules for mechanical minus 1,908.2 joules for kinetic. And when I do that, I get a potential energy of 1,091.8 joules. Okay. All right. So that gives me my potential energy. And when it's kind of funny, when I look at the question on page 13, question number 4 of your booklet, I realize that it's asking for just potential energy, in which case I could stop here and just make sure I have the right number of significant digits. I should have 3. So really I could round this to 1.09 times 10 to the power of 3 joules. But in my own notes, I had written a note to myself to say, let's calculate the height rather than the potential energy. I wanted to show how we can make this question a little bit harder. So while this would be a fine answer to the question on page 13 of your book, it doesn't answer the question that I'm asking here. All right, so let's take it one step further where we want to find how high this particular athlete jumped. So here, let's take a look at what we know. We know now that our potential energy is 1,091.8 joules. We know that this person's mass is 55.0 kilograms. We know, as always, that gravity is 9.81 meters per second squared. And this question is asking us for the height. All right. So we know that to find height, we're going to go height is equal to our potential energy divided by mass times gravity. My potential energy here is 1,091.8 joules divided by 55 kilograms times, you can almost read that, hey? Times 9.81 meters per second squared, okay? And when I put that in my calculator, what I get as an answer is 3.54 meters. And double checking my significant digits, every original number I had 3 significant digits. So this here would be the correct answer for how high this athlete jumped, okay? So these questions seem confusing, and there's really only 2 ways to ask them, okay? I can give you the starting velocity of an object on the ground, like I did kind of in this case, right? And then ask you how high the thing jumped to or how high it went. Or I can give you the object's starting height and ask you its final velocity as it hits the ground. There's no other way to ask this, okay? I can't ask you what its mass was at the beginning versus the end because its mass can't change. I can't ask you what gravity is because gravity can't change. So the way these questions work is I'll always either give you the height and ask for speed, or I'll give you the speed and ask for height. And the best way to solve these is to try and find the type of energy that you can, whether that's potential or kinetic, based on what it's given you. If it gives you mechanical energy on top of that, then you can use that to find the other one. If it doesn't give you mechanical energy, that's probably because it starts with all potential or all kinetic, and it's asking you for the other one, okay? These questions are tricky. I'd like you to try pages 13 and 14 of the booklet. That will finish the book. You should also, and I recommend this of everyone, it doesn't matter how well you're doing with this, try the mechanical energy boot camp. These questions are not easy. They take a lot more intuition. They take a lot more math savviness to make sure you understand correctly. All right. I will talk to you guys about this on Thursday. I hope you guys have a great day. Thank you for watching the video.